Happy Monday, everyone. So it's actually the second to last lecture today. Does everybody know that? Alright. Because in 1 week there's a bank holiday, if I understand correctly. And then in 2 weeks, or a week from Friday, there's something called the Project Demonstration Fair. So I'm the organizer, otherwise I might have lecture on that day, lucky you guys. So I won't have. I thought about it though. Attendance register, another one. Any questions about anything before we get started? That means everybody's happy. I am picking up a psychic wave though. Somebody's thinking about asking a question, but they're too afraid to. That's why I have psychic powers to help. You know, this is good practice for me. So somebody is thinking, have you started assessing assignment 2? Who was thinking that? I'm sure there's. Oh, see? The universe is connected. Everything is connected. There's no question about it. The answer is yes, I have. And then somebody is thinking, what do the scores look like so far? Well, my psychic powers are really hot today. And they look good. They look good. The same thing happens every year. Like, before the assignment deadline, everybody's like, I'm dying, and I'm crying, I can't get to sleep at night because I can't do this assignment. And then when I correct them, somehow they're really good. Average looks like a 70-ish so far. Using my psychic powers, I think the average is going to be somewhere around a 70 again. It's always the same. You have to be really strong to do this job. By the way, we all have psychic abilities, everybody. It's just who is interested and who wants to develop them and who wants to pay attention to them. And science is catching up. I just watched an amazing documentary, ridiculously amazing. It's called The Gut, Our Second Brain. Has anybody watched that? If you haven't, I highly recommend it. We talked about it already. Oh, such a good one. Such a good one. I won't talk about it now because I will get too passionate and I won't be able to stop. Can anybody tell me what they see on the screen?
Streamline integration.
Thank you, Carlo. Yes, this is just a fun kind of. I hope it's pedagogic, but it's like a video that illustrates some of the aspects of streamline integration, not everything, but some of the aspects. So that black ellipse is the seed position in a vector field, and then the animation is the streamline as it's being traced through the vector field. Anybody know what the box is? Carlo, what do you think the box is?
Some of the various vectors, like what is it, RK4 or something?
It's not the RK4 vectors, it's the original data sets. It is the data samples at the vertices. So the data samples are stored on a 2D Cartesian grid. And the box are the 4 data samples that surround the current streamline position. So in this case, in last lecture, we did evaluate the vector at every position, but it was analytical. Here we evaluate the vector field at every position along the streamline, But we do that using interpolation. That's the more common case. So it's one step of the algorithm is, okay, which cell am I in? And when I have a cell, I'm in a given cell, I look at my 4 vertices, surrounding vertices, grab the vectors there and interpolate them, use them for interpolation. And then that's how I derive the vector sample at the current streamline position. So this is showing some aspects of that process. And those edges there, the red edges, are the actual glyphs, they're vector glyphs that point in the direction of the 4 vectors at the corners of each cell. Yeah. So they're pointing in the other direction. These are pointing in the forward direction, right? Because the streamline is going that way. The integration and the vector field direction match. But we saw here that they're actually pointing in the other direction. That is backwards integration. So you can do forward, this is backwards integration because the vectors are pointing backwards. So we're just multiplying the vectors by -1 in that case to confuse you. It's because we can trace a streamline forwards from a seed position and backwards to get a complete streamline, right, through the whole vector field. So that's that. Anybody know what's happening here? Anybody want to take a guess? What's happening there? I think some people do know, but they're just too afraid to say. How about Benjamin Bonzer? Ben, what do you think is happening here? Use your psychic powers. Can you see that far?
Yeah, the point it was getting stuck at the point.
It's getting stuck.
The most I can think of is possibly it's just getting stuck within a loop at that point. Or
Any reason why?
Maybe I don't know how best to explain that.
Anybody want to help Ben? No, just let him suffer. I will help you. This is called a sink, or a critical point. So the vector field is 0 there. It gets in the sink and it reaches a 0 point, and then it stops, because if the velocity is 0, it has nowhere to go. There's no forward path anymore. So it sort of circles around due to numerical approximation a little bit around this vortex, but then it hits a maximum number of integration steps and just stops. So it's getting sucked into a vortex. That's what's happened. Sucked into a vortex. So this video is on Blackboard. I should update this. I should put this on YouTube actually as well. This is produced by a very talented postgraduate student by the name of Tony McLaughlin. He was experiencing some bugs while he was doing it, and so I said, can you please produce a video that shows these properties? And he did, which is here. And then I thought, oh, it's so nice. It's actually like a teaching video. It's really a very pedagogic kind of video, because it brings the integration process to life, the streamline integration process. Okay, there's that one. And so we talked about streamline integration last time. That's to trace one streamline. Now we can talk a little bit about streamline placement. So once you can trace one streamline, how do you actually place them in space? So there's one algorithm to trace a single streamline, but there are other algorithms to place them in 2D, 3D, and in this case it's 2.5D space. And you'll notice that these streamlines have a kind of property to them. They're almost evenly spaced. So there's a space between each of the streamlines, which is nice because it's predetermined. In other words, you can select the density or the amount of space between them. And that way you get complete coverage of the flow. You don't have to worry about necessarily missing some features if a streamline does not intersect with a feature. Right? So they're between a threshold distance of each other. So we're going to talk about today how to create evenly spaced streamlines, or more accurately, how to approximate evenly spaced streamlines, because they're not perfectly evenly spaced, but they're approximately evenly spaced. And there's definitely a copy of this video on YouTube already. So let's talk about that. So we had the non-trivial lecture last time with numerical integration of streamlines. And different integrations. So now we are looking a little bit more deeply at streamline placement and other streamline properties. So streamlines placement in 2D, these are the evenly spaced streamlines, right, in 2D. And these are, there's no upstream and downstream direction information here. So you cannot tell if the flow is moving this way or this way. So orientation. Here you can tell by the semi-transparency that the streamlines are actually moving in that direction. You can see the downstream direction if you add some semi-transparency. There are other kinds of curves for time-dependent data. So streamlines are the term used for tangent curves in steady-state data. The data does not change over time. But there are other kinds of curves for time-dependent data. One is called a streakline, and another one is called a pathline. Actually, it's easier to talk about a pathline first. A pathline is a curve that's everywhere tangent to an unsteady flow field. So the definition is the same as a streamline, except for unsteady flow. And the integration is very similar too. So imagine we're standing on a bridge, like we always like to stand on bridges, right? When you cross a bridge, you really want to stop, don't you, and look over the edge. You get the impulse. I always get the impulse to stop and look over the edge. And take photos, right? I did it just while I was in the Netherlands just a week ago or whatever, and I stopped on the bridge and I took a beautiful photo. So imagine you're crossing a bridge and you see a river below you and you get the urge to take a photo of the river. You take a photo and that's your vector field. Or the surface, the vector field of the surface. If you were to take a massless particle and drop it in there, like just as an analogy, a piece of popcorn, like it's kind of almost massless compared to the density of the water. If you dropped a piece of popcorn, it would hit the water, the surface, and then it would trace out a streamline in your photo. Like that's a steady state vector field. A photo of a vector field is a steady state. It's not changing over time. So if you drop the popcorn in there and then start to integrate the path using numerical integration, trace the streamline, it's that same line that that piece of popcorn would follow if it was allowed to move along the vector field. Now, instead of taking a photo, forget the camera and just look at the river and drop a piece of popcorn. The river is moving, right, because it's time dependent. The path that popcorn traces is a path line. If you drop one piece of popcorn in there and follow the path that it traces down the river, that is a path line, or an approximate path line. So it's a curve that's everywhere tangent to unsteady flow field. Does that make sense? So one is a photo of the river, because it's not changing over time, but it's still a vector field, it's just not changing. And the other one is like a video of a river, it's changing over time. And those two paths are not going to be the same. They might be similar, but they're not going to be exactly the same, because one's steady state flow and the other one's unsteady flow. Does that make sense to anybody? I think it's easy. I don't think that's complicated. It might be a little bit complicated to compute, but just to understand what it is, I don't think it's too difficult. Then the streak line is another variant of a curve. Imagine you have a bucket of popcorn now. You have a river, and the river is flowing, and you take a piece of popcorn every half of a second, and you drop it into the river. Assume there's no wind, by the way, like blowing the popcorn around, it just falls straight down. Now, you're dropping popcorn into the river every half of a second. So it hits the river, it moves for a half a second, right? And then the next one lands, and it also moves for a half of a second. Drop n pieces of popcorn and attach them with a curve, with a polyline. That is a streak line. That's a little bit confusing, but you can think about that. That is also analogous to taking some perfect source of color or dye, like imagine a tube of dye, and just slowly squeezing it into the river, right? The curve that dye traces out is a streak line. It will, that's the idea, at least. The problem with that analogy is that the dye will spread, so it will model diffusion. Diffusion will happen. Imagine the dye doesn't spread though, it just is translated with the flow only. Like it preserves its kind of that property that makes it connected as a line or a curve. That's a streak line. So we can color code the streamlines based on some property. It could be velocity magnitude, it could be pressure in the case of CFD, or it could be temperature in the case of CFD, or any other property of the flow that we want to look at. And here the streamlines have been placed manually, right? Somebody has determined that they want to see the flow behavior below this aerodynamic vehicle, so they placed streamlines right below. These are illuminated streamlines, so they are, you can see that there's no shading here, so it's hard to perceive depth here. If we could rotate this, then the depth would come out. But right now, the only depth cue here is occlusion. So I can see that this streamline is in front of that one due to occlusion. But generally speaking, the depth cues are hard to perceive. Here, the perception is a little bit enhanced because the streamlines are a source of light. They're illuminated. So they look like they're fiber optic, don't they? It could be called fiber optic streamlines. Yeah. So those are some properties of streamlines, 3D streamlines, and streak lines, and path lines. And it may take a little bit of time for the path lines and streak lines to sink in conceptually, because it is confusing. It is confusing. Try to remember that the path line is associated, well, it might help to remember that the path line is associated with one massless particle dropped into an unsteady flow, and a streak line is associated or formed by several particles dropped into the unsteady flow over time and connected together. Those are two different paths, actually. So let's talk about streamline placement in 2D because this is a very common test question, especially on previous exams. So in that video we saw that at the beginning of the lecture it started in the bottom left-hand corner, the seating positions, and then they just moved over, like 1 unit, another unit, another unit, another unit. That was the seating algorithm. Just start in the corner, see the streamline 1 unit away from the origin, and move 1 unit to the right, and repeat. That's a rasterized streamline seating strategy. That is like the default seating strategy. Right? Or it's also, in this context of this slide, it's a regular grid. A regular grid is used to seed the streamlines. And when you do that, this is kind of what you get. 1, it's kind of ugly. 2, the streamlines overlap, so you have lots of redundant computation. And 3, the spacing or the gaps is a little bit erratic, so it's possible to have very big gaps and maybe miss some features. This is a very different algorithm, right, of the same data set that's using the evenly spaced streamlines algorithm. And that's what we're going to try to talk about, how to do this. And I would say it's non-trivial. It's not a trivial thing to understand, actually. I wouldn't say it's really difficult, but I wouldn't say it's trivial. I would say it's non-trivial. So the idea to create evenly spaced streamlines is that streamlines really shouldn't collide. That's the idea, like that's the basic premise. Like if they collide, it means they're overlapping and it causes aesthetic problems and extra computational problems. You could also say you're oversampling the vector field, that you're slowing down the performance. Right? That's the left image. In the left image, the streamlines had no knowledge of each other. You just trace a streamline and you don't think or know or care about any of the other streamlines, any pre-existing streamlines. Basically, the evenly spaced streamlines algorithm is saying, okay, let's make streamlines, let's add some knowledge that makes them aware of each other. So when I'm tracing one, it's looking out for other ones. Instead of just blindly going until the end, it actually is looking out for other streamlines and terminating if it gets too close to another streamline. That's the idea. Now, how do you actually do that? So that means you have to make the streamlines aware of each other. So the idea is to choose a seed point, and the seed point is not just along a regular grid anymore. Instead, it's from an existing streamline. So you choose a seed point that's some small distance, d-sep, away from an existing streamline, as opposed to just on a regular grid. And then you integrate the streamline forwards and backwards until there's a terminating condition. We're going to talk about the terminating conditions. But one of the terminating conditions is until you get too close to another streamline. So there are 2 important parameters. One's the start distance, that distance away from the existing streamline. And then this is the termination distance. How close do you want to come to another streamline before you terminate yourself and stop integrating? This is what the pseudocode looks like. Actually, I think what we're going to do is we're going to change the order of the slides and do this one first. So step 1 is to choose any point, a random point, that's fine, and trace the first streamline. So the first streamline, you can trace that wherever you want. let's imagine that this is the first streamline. So a random seed was picked, and then the streamline was traced forward and backward. So that thick one is the first one. So just choose an initial random seed. Doesn't really matter. Because the first one's not going to collide with any others. Now what about the next streamlines? So it's a search process. We're going to perform a search through the space based on the streamline itself. So starting at one end of the streamline, for example, we're going to search on both sides, left and right, for empty space. So we search and we find, for example, well here we could have just found our first empty space here, but in this diagram, the first empty space we find is here, and it's a distance d sep. So we actually find an empty space and we see a new streamline in that empty space because there are no existing streamlines already. And this d really should be d sep, by the way, not just d, but it's the separating distance between streamlines. So there's our new seed. We found an empty space, we put a new streamline seed. If there was already a streamline seed there, we wouldn't see this because it wouldn't be an empty space. There's our new seed. Then we forward integrate the streamline there and backward integrate it, or vice versa, it doesn't matter. And we put it into a queue for future processing. In other words, for future searching. And we go back to our original here, and we continue the search for empty space. So we start searching, but look, this one is here now, and it's too close. Right? We don't want to we can't now see another point here, because it's too close. There's a streamline there now. So we keep going, and then we test again until we find enough empty space, right? Because the space between these two is increasing. So we find a new empty space here, and we see the new streamline there, and it's the distance d away from this one. So we do the same thing. We forward integrate and we backward integrate a new streamline, and we put it in that queue that we mentioned just 2 seconds ago, for future search process, a future search process. And we keep going. So we're here, we seeded, we're here, and then we find an empty space. So we see a third streamline. We forward and backward integrate. This one stopped, right? Because it's getting too close. It terminated itself. This one terminated itself because it's getting too close to the existing streamlines already. These terminate because they reach the edge of the domain or the maximum length. So we trace, and then we continue the search, right? We find a new one, forward, backward integration, continue our search. We're not finding anything due to the previously existing streamlines until we get to here. And then we forward and backward integrate and keep going, right? And make sure that all our streamlines, all our seeds are d-sep away. So in this illustration, we seeded 1, 2, 3, 4, 5, 6 new streamlines along the empty spaces of that streamline. So we're searching 2D space in a streamline-oriented path. All of the new streamlines are put in a queue, and we repeat the process. That's it. That is the algorithm. So the next step is to take this streamline, this is the second one, this example, out of the queue and repeat the exact same process. It's not illustrated here, but imagine we start at the beginning of this streamline. We would see the next one here, because it's an empty space. Seed it, forward integrate, backward integrate until we got too close to an existing one, and then continue the search down. And maybe we would have to get, we can't see it anywhere on this side because we would get here maybe, and then find a new empty space. Forward, backward integrate. And maybe we find a new empty space here, forward and backward integrate. And those new streamlines get put into the queue. This is what the pseudocode looks like. So I thought it would be useful to look at the picture first before looking at this. So compute the initial streamline, just can be a random one, put it into the queue. Current streamline equals initial streamline, and this is a while loop, right? Until all the streamlines are processed. Try to get a new seed point which is descent away from the current streamline. That's that search process that we're talking about along the streamline. If we find one, if we find an empty space, then seed the streamline and put it in the queue. Right? Seed a new streamline, compute, integrate forwards and backwards, and then put it in the processing queue. And if there are no more streamlines to process in the queue, then we're finished. Because once we've processed them all, we're finished. Otherwise, take the next streamline out of the queue and do the same thing. That's the process summarized. When do we actually start terminating? There are a few terminating conditions. So this is the first terminating condition, like we mentioned, is if one streamline gets too close to a pre-existing one. That's this distance called d-test. No pun intended. I've been saying that term for a long time now, and I never got that pun before. Like, that's the first time. It's the psychic powers. Very active today. That's the first terminate. If we hit the edge of the boundary, obviously we terminate. This was in the video, right? If we hit a fixed point, velocity approaches 0. When a streamline collides with itself, we'll stop. And if a streamline integrates a certain maximum number of steps, that can happen like in that case that we saw in the video. Actually, that was this case. Because the streamline got too close to a fixed point, it started going in this erratic circle pattern, so we terminated. It can also happen in the case of a spiral. Like, streamlines can enter a spiraling pattern, and then they can just take forever to compute. So there's a special clause in there that just says terminate after a certain maximal number of steps. A lot of people, when they're writing software, forget this case. And a lot of software crashes because people forget, software engineers just forget this case. This isn't just about streamlines. This is for every piece of software in the world. A lot of people forget this. And that's one of the reasons why software is so unstable nowadays, amongst many other reasons. Here are some parameters, like the descent parameter. What happens when you change the descent parameter? So the descent parameter is a user option. So the user can change that. So this is 6% of the image width of the image. This is descent at 3% of the width of the image, and this is at 1.5%, so they get more dense. there's a trade-off between how fast you can do it and how dense the coverage is. Now, this is what happens when you vary d-test. That's the terminating distance. How close are you allowed to come to another streamline before you terminate? And this is when d-test is almost the same as d-sep. Right, 0.9 is like 90% of d-sep. So that means they're almost the same. And look, you get short streamlines, a lot of short ones, which isn't very nice, right? The shorter the streamline is, the less of a streamline it is. The more it's just like a glyph. So in order to prevent the shorter ones, we make d-test a little bit smaller, like, for example, half of d-sep. And then we get longer streamlines rather than those tiny short ones. We can enhance the streamlines, right? We can add something called tapering. Anybody here, like, ever do drawings or paintings or artistry? Nobody here has ever done any artistic things ever? Huh? I mean, we all did painting in school, didn't we? I certainly did. Drawing and stuff. Anybody know what tapering is? I don't think my teachers have. No. Yeah, it is related to gift wrap, actually. But tapering is making the ends of the streamlines thinner. So they're thicker in the middle, and as they get closer to the endpoints, they get thinner. That's the tapering. It's aesthetic, essentially. And we can add the direction of the flow with glyphs. Here we can now see that the direction is pointing this way with the directional glyphs. And here we can actually see it's pointing this way. And the original paper is on Blackboard. So if something in my explanation didn't make sense, you can have a look at the Blackboard. And we can also look at, now have another look at Ben Spencer's amazing work. This is the evenly spaced streamlines algorithm again. Now you'll see it makes more sense. It says what d-sep is set to and what we're looking at. Does anybody know the difference between this algorithm and the one we just saw on the slides? Anybody notice the difference? That would be a good test question, actually. The one here in the video is for surfaces. The one in the slides is for 2D planes. So this is the evenly spaced streamlines algorithm extended to arbitrary surfaces. And that was an unsolved problem when we started teaching this module. And then Ben Spencer, a student here, solved it and published a great paper about it. And this is the video he produced for it. Very, very talented student. So this is showing animation, right? So we can see the downstream direction of the flow, not just the upstream. Those are compression artifacts, though. You can see some aliasing due to compression artifacts. Those are not really a result of the... This is tapering. That's the underlying mesh, the surface mesh. And those are illustrative streamlines with tapering added. So you can see the underlying vector field is very complicated here. It's one of the challenges with the algorithm. That's a non-trivial mesh, vector field mesh underneath. This is the user changing decept, the decept parameter interactively. This is actually showing the seed points, and in this case there are two kinds of seed points. We have to add a new kind of seed point because of the we're seeding on surfaces. We have to make sure we get each part of the surface, so we need two kinds of seed points. This is about perspective foreshortening. Now there is no perspective foreshortening in this clip. That means that evenly spaced property is held, preserved, regardless of the depth. Here, as the depth increases, decept also decreases to give that added feeling of depth. Right, that's inside a cooling jacket. Now we know what it feels like to be inside a cooling jacket. And there's obviously a copy of that one on the Database YouTube channel. And I'm pretty sure there's a presentation of that as well on the YouTube channel, if anybody wants to see it again. Any questions about that? Okay, now I guess we'll just have a little preview of the next lecture. Does anybody have an opinion about the next lecture? What we should talk about? So, I mean, I was going to talk about Flowviz Part 3 in the next lecture, because I don't think that anybody has been thinking about revision for the exam yet. Am I right about that? So, like, another option is exam revision, but I don't think that anybody has actually thought about exams or the revision because everybody's too busy. I will ask, like, you know, if Carla, you're the master's student rep? Or no, Teresa is. Okay.
I can pass that on.
Yeah, you guys can decide how you want that Friday to work, if you want. If I hear from the master's students in Rodri, like, we would rather have a revision lecture on Friday than a regular lecture, that's fine. But I don't think, last year that's what I did, but all the students were like, that wasn't very useful because we have not been thinking about the exam at all. Like, so they didn't think it was that great. And it's on YouTube, that one's still on YouTube from last time. And then we had another revision lecture before the exam, like an extra lecture where students prepared questions that they wanted answered, mostly previous exam questions. And then we had a real revision lecture, so to speak, which is also on the Database YouTube channel. It's a massive lecture. It's almost 90 minutes of just students asking previous exam questions, basically. Or other things. So I will let Carlo and Rodri decide how that goes. By default, it will be Flowviz Part 3, and we'll just have a quick preview before we stop. So the next part is about stream ribbon, stream tube, streams, and stream surfaces and flow volumes. So we won't have time to talk about all of these things in the next lecture. Probably we would get to like stream surfaces. So stream ribbons, how to compute stream ribbons, and then introduction to stream surfaces, flow volumes, stream tubes, and then stream surface construction. So we would introduce some more terminology, and then look at the stream surface construction algorithm, which is, you know, it has some things in common with the stream, evenly spaced streamlines. And if anybody's curious, there is a copy of this lecture from last time on the Database YouTube channel, if you're curious. This time it will be a little bit better, but the old one is, no, actually, the old one's not there. because something went wrong. I was using a laptop to record the lecture and it crashed. So that one is not there, actually. So. Okay, are there any questions about anything? Everybody's really sad that the semester is coming close to an end, like crying and stuff. Like, I understand, I cry too at the end of every semester. But, you know, we're all still alive. You know, I'm still in room 508 of Faraday Tower. And I even get visitors sometimes. By the way, I'm not joking. I do get visitors sometimes. And I got a visitor very recently from a company here in Swansea. And he's doing data visualization at his company. And he is using all the principles we applied here. And he gave me a demo, and I was blown away. I was like, wow, this is really good stuff. The company, of course, loves it. And his salary, he can watch his salary go up. These are very, very transferable skills that industry is dying for. Because every industry has this crazy amount of data that they can't understand. Every industry. There are no exceptions generally. And that includes Swansea University. So it's really a ubiquitous problem. Highly transferable skills. Very, very valuable in industry. Okay. We'll stop there for today. Happy Monday. Question? Yes. Not only at the conceptual level. So if you look at the tutorials for assignment 3, you go into a long explanation. Well, not that. You go into an explanation of the difference between concept and implementation. So for the previous work, you only understand the previous work at the conceptual level, not the implementation level. So you see in the related work section, you try to identify the one or two most importance. And then you summarize them in 1 or 2 sentences at the conceptual level. So for example, we just summarized a paper called Unitary Space Streamline. Right? The conceptual summary of that is, this is an algorithm to place streamlines evenly from each other on 2D planes. That is the conceptual summary of it. It's like a 1-sentence summary. It doesn't say how it does it. It just says what it does and why it does it. So conceptually, it's what and why, and the how is ignored.
The 2 pages for points.
You will get some points off, yes. Because part of the challenge is how to condense it. It's part of the challenge.
If I don't, like right
If you go over, that means you have too much. So that means you've included too much information. If you go more than 2 pages.
I'm sure.
Happy Monday?
I was a bit late to it, but is it possible I could get a two-stage paper for something?
Yes.
They did send an email today about that was like half an hour for lecture.
What time did you send me?
It was literally about half full.
Okay, I can give you one right now.
Cool. Does that include weekends?
If you go to my webpage and click on publication lists, you can choose one from here.
I missed half the Saturday.
I would choose, let's see, number 38.
Rather my hand.
Yep.
Number 38.
Number 38.
38.
There was a whiteboard marker, so be careful.
It's not going to forget. Cheers,
The smart guys.
Because you've lost a couple of podcasts due to
Drunken adventures, I know.
is the exam going to be on things covered in lecture, or just things on Bibles? Because it's still,
But there won't be something in the exam that's not mentioned in lecture. Because I think Blackboard has a few extra things.
because it's like a data mining lecture.
That was a guest lecture from a past year. If you want to know more, like I'm going to give hints on how to prepare for the exam on
Did
Friday.
you give any official Excel document?
Exactly, which I just updated today, by the way, a few hours ago, like just after lunch.
So if you think on that, it's going to be
That's right.
potentially beyond exam.
Exactly, yes. Anything we talk in the lectures about, and anything in that spreadsheet, but they're the same. Everything we talk in the lectures. So the revision lecture, if I gave a revision lecture on Friday, the only thing I would do is go through the slides and write down all the terms that you need to know. That's it. Which is what that spreadsheet is. It's just me going through the slides and writing down the terms.
Just didn't want to like make sure getting to exam then this is a lecture on that you didn't say.
Yeah. So yes, there are a few extra lectures on the. Maybe I should put a note on there. But you got the lectures on the database YouTube channel, so those are the important ones. The guest lectures are not. The guest lectures, by the way, have a different naming convention. You'll notice that one has the word Gang as the name instead of Larrabee. So Zhao Gang gave the lecture. That means it's not on the exam.
One, two, 3,